In this video, we're going to go through cash flow mapping, keeping the variance constant. So I'll get the lecture notes, share my screen. And we are here, making sure the cash flow map doesn't change risk. So as with the present value constant mapping, which can be anything, any proportion of the single cash flow at maturity Ti with present value Xi can be mapped to the two immediately adjacent vertices T1 and T2. Doesn't matter what P is, it always works that the present value is unchanged. And as before, well, I don't know where I introduced this already, the spot rates at these maturities, Ri for the spot rate at Ti, R1 for the spot rate at maturity T1, and R2 for the spot rate at maturity T2. But the difficult thing is to choose P so that we don't change the risk of the portfolio. So the variance needs to be the same before and after the mapping. We're going to capture risk with variance. Obviously, standard deviation is constant if variance is constant under the mapping. So we're going to work with the variance. And so we've got an amount Xi that is coming at maturity Ti, and the risk is associated with changes in the interest rate at maturity Ti. So it's that capital delta you see in the center of this slide here will be typically when we have daily data on interest rates, it will be the daily change measured in basis points in the interest rate at maturity Ti. And the variance of Xi delta Ri on the left-hand side here can also be written as Xi squared, because that's not a random variable. Xi is some present value. So Xi squared times the variance of delta I. And I'm going to, for short, denote the variance of delta I by sigma I squared. So that down on the left at the bottom in red, you'll see Xi squared sigma I squared. Now, the mapped cash flow, where P goes to T1 and 1 minus P goes to T2, means that the total present value, proportion P goes to T1, the amount of present value is P times Xi. That's what you're going to map to T1, and then the rest, 1 minus Pxi of that present value, is mapped to T2. And so you've got two components now to the risk. And now P and Xi are both not random variables, so we can take them out. And it's the variance of delta R1, which we're going to call sigma 1 squared, and the variance of delta R2, which we're going to call sigma 2 squared, that we need. But also, because we've got the variance of a sum, we need to know their covariance between delta R1 and delta R2, and we're going to call that sigma 1, 2. So applying the usual rule for the variance operator, we've got P squared Xi squared sigma 1 squared plus 1 minus P squared Xi squared sigma 2 squared plus 2 times the product of the coefficients, 2AB, right? So A is Pxi, B is 1 minus Pxi times the covariance. So that's what we need to make variance invariant under the cash flow map. We have to choose P such that this equation holds. Now, Xi squared occurs in every term. There's Xi and Xi there in the end. So we can cancel that and we get a different equation. This one, which is a quadratic equation in P. And we can, I haven't done this, but we can rearrange, so we can write it as AP squared plus BP plus C equals 0. just like ax squared plus bx plus c equals 0. And you know the solution is x is minus b plus or minus the square root of a squared minus 4ac all over 2a. That's a formula for the roots, two roots, because you've got the plus or the minus of a quadratic equation. So we can calculate those in the workbook, which I'll go through when I finish this video. In the workbook, actually, we put in the correlation. It doesn't matter. As long as we know the two standard deviations, given the correlation, we can then get the covariance, because the covariance is just the product of the two standard deviations times the correlation. And we'll see in the workbook that typically we're going to get, obviously, two solutions. It's a quadratic equation in P, but only one of them can be a proportion, because only one of them lies between 0 and 1. So I'm going to set this example up in the workbook. You've got a cash flow, present value xi is 2 million. Ti is 265 over 365, because it's always measured in years. T1 is 0.5, T2 is 1 in years. And we've got sigma 1 and sigma 2 are 75 basis points and 90 basis points. And the correlation is 0.75. We've got sigma I here is 85 basis points. What is P? How much in present value terms is mapped to each vertex? So I find P, and then I multiply P by 2 million, because that's what xi is. Remember, pxi and 1 minus pxi are the amounts in present value terms that's mapped to each vertex. And so this is the equation, 85 squared, that's sigma I squared, equals sigma 1 squared times p squared. This is just putting in the numbers in this equation here. And that, when you turn it all around, gives us 3,600 p squared minus 6075 p plus 875 equals 0. And in the workshop, we'll see there are two solutions, but only one of them, and that's p equals 0.159 on 15.9%, is between 0 and 1, and the amount you map is 2 million times 0.159, which is $318,035 goes to the 6 months vertex, that's T1, and the rest, which is $1,681,965 goes to the 12 months vertex. Let's have a look at it in the spreadsheet. So these are red, they're parameters, we can change them. That's the volatility at sigma I, and this is sigma 1, sigma 2, rho 1, 2, and then how you calculate A. I didn't put that formula in the lecture notes. It's just a little bit of algebra to find out what is the coefficient of p squared. That's A, coefficient of p, constant, discriminant, that's b squared minus 4ac, and then the solution is minus b plus the square root of b squared minus 4ac all over 2a, and the other solution is minus b minus the square root of b squared minus 4ac all over 2a. That's the quadratic formula there. So this is the solution we're going to have in this case, but it depends. When you change parameters, it might be solution 1 that you choose. And this is the proportion, and the amount, this is the present value of 1 unit of cash flow. But if the cash flow, I don't need to know any interest rates or cash flow amounts or anything like that that we have for the PV and PV01 calculations. They don't come into it. All we need to know are the volatilities and correlations of these interest rates. when you look at the formula again in the lecture notes, this one here, sigma I squared, sigma 1 squared, sigma 2 squared, sigma 1, 2, there's nothing to do with the timing of the cash flow at all. It's just the standard deviations and the correlations that we need, and then or the variances and the covariances that we need, and then we can solve it. So the fact that it was at 265 days really doesn't come into it in the solution. So that's it.